Hi there. We are looking at Unit 5 from Algebra 1, Illustrative Mathematics, Imagine Learning. Let's get started with the Lesson 1 practice problems. Number 1 is just a multiple choice. It wants to know which expression equals 2 to the 7th. So they're really just testing you here to see if you know what an exponent stands for. So go ahead and choose or select your answer that you think would be the expanded form of 2 to the 7th. Is it adding, multiplying, or just times 7 or plus 7? What do you think? The next one wants you to actually plug in. When evaluate means to plug in a number. 3 times 5 to the x means 3 times 5 to, instead of x, we write to the power of 2. So what we want to do here is actually plug this into a calculator where that dot in the middle is like saying 3 times 5 squared. Now, I have a scientific calculator, and in class we have scientific calculators. Do you have one at home that you can use that has a power button to get the squared in there? Otherwise, you're going to want to go click on the link attached to Google Classroom for Desmos Scientific Calculator, and we're going to go type it in here. So 3 times 5 to the power of 2. We type a 3. Times is over here on the side. 5. Now to get power of 2, you have two options. You can just do squared or any power. A to the b is represented here. And to make sure that you got it right, make sure it's up in the sky from the 5. So 3 times 5 squared, 5 squared is 25 times 3. The answer is 75. So they wanted you to actually plug that in. And we got 75. So we're really testing to see if you know how to use the calculator to get a power button. Next, the graph shows the yearly balance in dollars in an investment account. So notice this curving that's happening on the graph. And what is the initial balance in the account? So they're asking for that vertical intercept, initial balance in the account. You got it. It has 1,000 in the account to start. And it says, is the account growing by the same number of dollars each year? Now, it kind of looks like from here to here, from here to here, it's sort of going in a straight line. But then what happens as we go further? Do you see that curve start to happen? What that means, if it's not staying in a straight line, is that the jump is not constant throughout the entire graph, but it is still such a small growth that it almost looks linear for a time. So is the account growing by the same number? No. It almost looked like it until it starts to curve, which means it has to be different each time. Now, when I'm doing these homework hints, what I write is just sort of talking you through the problem. You should be writing your own response in your own words to each problem, and then maybe watching the video if you have any questions on some. A second investment account starts with 2,000 and grows by 150 each year. Sketch the values of the account on the graph. So let's get a quick idea of what's going on here. So starts with 2,000. So at the beginning there was 2,000, and then grows by 150. So 2,150. 2,300. What am I doing? I'm adding 150 at each step, et cetera, et cetera. You can go ahead and grab a calculator and keep it going if you want to, but let's go graph some of these dots. So 0, 2,000. Oh, let's not use the same color. It's going to start somewhere like right there. 1, 2,150. Somewhere like right there. 2, 2,300. 3, 2,450. Now, it's kind of hard to see because I'm using such a big blob there. Let's go a little bit more refined. But when we're adding 150 each time, it is going in a nice straight line. I don't know, something like this. where it's going to look like a straight line because it's going up by the same amount each time. So how does the growth of balances in the two accounts compare? The growth in the first account is going up by a different amount each time and creates a curved graph. The growth in the second account is going up by a constant rate of change of the same amount each time and shows as a linear. That's what we did last semester, linear functions. So now we've got this new curve thing going on that we've got to deal with. And so we're starting to notice some things about that. Okay, so part C was us adding the graph of like that straight line, do your best to make it look straight. And then part D is typing about the change that you're noticing of the growth. All right, Jada rewrites 5 times 3 to the x is 15x. Do you agree that these are equivalent expressions? Explain your reasoning. Well, this is a common error that we see as teachers where we take the 5 and the 3 and multiply them, but be careful. Let's plug in some numbers to see if this works. What is 5 times 3 to the first power? Well, 3 to the first power is 3. 3 times 5 is 15. And if I plug in 1 to the other equation, I also get 15. So at first glance, I might think, oh yeah, these are equivalent. But hey, it's got to work for all values. What about 5 times 3 squared? Well, 3 squared is 9. 5 times 9 is 45. Now let's do the other one. 15 times 3. Well, 15 times 3 is 45. So far, is it working out? Okay, yeah, it is. Let's keep going. 5 times 3 to the third would be 5 times 27. I got to get my calculator out for that one. That's 135. And then 5 times, 3. Oh, I'm sorry, you guys. I see the error I made up here. If we're plugging in a 2 right here for squared, then I need to plug in a 2 right here, and already it proved that it was wrong. And here when I plug in a 3, 5 times 15 times 3 is 45, and that does not equal the other equation, the other expression. So basically, we just showed with 2 instances. When I plug in 2, when I plug in 3, they did not equal each other. So by showing a counterexample, that helped explain my reasoning. So are these expressions equivalent? Do they equal the same thing? Only when I used an x of 1. If I use an x of anything else, no, they are not equivalent because they yield different results when I plug in different x values. Again, writing that in your own words based on the work that you showed. All right, number 5, investment account 1 starts with a balance of 200 and doubles every year. Investment account 2 starts with 1,000 and increases by 100. Notice these are very much like the classwork. How long does it take each account to double? And so You can do a table to see like how long until it makes the next thing. So for example, it starts with a balance of 200. Oops, need my text box. So I'm putting part B kind of like over here. Account 1 starts with 200 and doubles so by year 1 it's already doubled. Account 2 starts with 1,000. And if we need to see when it's going to double, we're going to be adding, how much are we adding? 100 each year. So 100, I need to do that 10 times. So 100 times 10 would be 1,000, and 1,000 plus 1,000 would finally be 2,000. So how long does it take for each count? So after 10 years for account 2. How long does it take for each account to double again? So account 1 doubles again the next year. And likewise, account 2 takes many years to double. So let's see how many. So we've got this 2,000. We want to know when it makes 4,000. So I need to add 100 how many times? 20 times. So 2,000 plus 2,000 is when it would double. So it took account 2 20 years, or another 10 years from the original. I'm going to put the answer for part B down here because I keep running out of space. Finally, how does the growth in these two accounts compare? The growth in account 1 is multiplying by 2, and the growth in account 2 is adding 100. The growth in account 1 is multiplying by 2 repeatedly each year, and the growth repeatedly Okay, again, in your own words, do your thing. Okay, study of 100 recent high school graduates investigates a link between childhood reading habits and achievement in high school. The participants are asked if they read books every night. And so on the left, we've got, do they have an A average, a B average, a C average, or a D average in school? And then there's a column for, do they read books nightly or did they not read books nightly? So question 1 says, what does the 21 in the table represent? So you would say something like, it represents students or participants that have a B average who read books nightly. Or you could say it in reverse. It represents participants who read books nightly who have a B average. But you basically need to put the combination of those two ideas together. And finally, let's go put the purple right here. For this one, the 10 in the table, what does that represent? That is students who have an A average who did not read books nightly. Or you could say students who did not read books nightly who have an A average. So go ahead and write out your own sentence in your own words about those comments. It's basically just reading a table. Lynn says that a snack machine is like a function because it outputs an item for each code input. Explain why Lynn is correct. Well, we know from last semester that a function is for every input, there's only one output. So if I push a button, A1 or 10, When I put in my money into the machine, it gives me a different candy or a different chips each time, a different snack. So because for every input, money, the number on the machine, I get a different output, it is true that it is a function. At a gas station. So by the way, that's going to be a sentence answer for number 7. Put it in your own words. All right, number 8, at a gas station, a gallon of gasoline costs $3.50. The relationship between the dollar of gasoline and the gallons purchased can be described with a function. Identify the input variable. Input means based on the input, the output is determined from that. So input is going to be the gallons, and then the output is going to be the cost. And so describe the function with a sentence in the form. We would say cost output is a function of the number of gallons. If I have more gallons, my cost goes up. If I have less gallons, my cost goes down, etc. Identify an input-output pair of the function and explain its meaning. So if I buy 1 gallon of gas, it costs $3.50. So my input-output pair would be 1, $3.50. If I did 2 gallons of gas, 2 times $3.50 makes $7. So 2, 7 would be another example. You make one up. You do 3, or you do 10, or you do whatever you want to do. Make another input-output pair. And that's part C. How'd you do? Homework is done.